Well, next up is Victoria Risk. She's coming from that side. Here's the pointer.
Great, thank you.
There's your text.
Okay.
And there.
Oh, great. Ooh, I should have worn my sunglasses. So, good afternoon. Thank you for inviting me to speak. This is the first time I have been to a Netnod meeting. It's also the first time I've been to Sweden. So, I came here actually with my daughter, and she saw some of the assembled crowd at the break this morning, and she said to me, "Mom, you're the oldest person at this thing." So I think that's actually appropriate because I'm here to talk to you about the oldest DNS software out there by 9. Pardon me. So I am represented by that little red figure in the middle. When I joined ISC almost 10 years ago, in October of 2013, we had only two primary developers, primary committers, working on Bind 9. We had one other guy who was kind of a junior developer who was mostly a QA person, but all of the rest of the DNS team was working on Bind 10. So at that time, they thought Bind 10 was going to replace Bind 9, and Bind 9 was essentially regarded as end of life. There was not a lot of effort being put into it. Not to downplay the skill of the two guys working on it, it was not a great investment on the part of ISC at the time. So the skull and crossbones there in the spring of 2014 represents our decision to end the Bind 10 development project. And unfortunately, because of our financial situation, at the same time, we also had to lay off about a third of the ISC staff. So this was really a very dark time at ISC. But since then, you can see from the crowd of blue and green guys, we have really recovered financially, and we have significantly rebuilt the team so that the little green men there are QA specialists on the current Bind team, and the blue people are software engineers. So we now have 12 people working on Bind 9, and it is significantly improved from where it was back in 2014. Back in 2019, Andre Suri, who's the director of the Bind 9 development team, was actually here at Netnod. He talked about a lot of the new features. This is far from a complete list of the features we've added since then. As the product manager, I'm all about new features. I've advocated for most of these new features. A lot of them were driven by the need for mitigation against various abuses in the DNS. That's really why we added the cookies, the minimal responses, serve stale is also a mitigation for major outage of authoritative providers, the response policy zones. A number of the other features were to improve the operability, particularly of DNSSEC. And then most recently, we've added support for all the new encrypted protocols and the extended errors. But in any case, I'm not really here to talk about the new features. As a product manager, I have to own up to a lot of mistakes. And I will say that a number of the new features that I thought were going to be great have turned out to really not be improvements. Serve stale, which was supposed to allow recursive operator to continue to provide access after the authoritative owner of the records had gone offline. This is something that came about after a big Dyn outage. I don't know how many of you remember that back in, I think it was 2016. Anyway, this involves keeping stale records around for a long time, extending the TTL and serving them, and it's actually really has tremendously complicated cache management. The NSEC aggressive use, this was another really good idea. It came from Jeff Houston. The idea was you already have the NSEC records, so you can synthesize negative answers without doing a query. Just analyze your NSEC records and see if you already know that there's no answer between two names, that you have, your query is covered by a negative record. Go ahead and synthesize that. But it turns out that doing all that analysis, even though you already have the data, takes longer than just sending another query. So that was not a big efficiency. I can't really argue against QNAME minimization. Obviously, privacy is a really good thing. But this has caused a lot of collateral issues. So introducing a new DNS feature at this point in the deployment of DNS, you have to realize that people have set up their DNS without expecting some of these features. So people have the client, the parent and the child zone on the same machine. QNAME minimization means you're doing twice as many queries as you would have had to previously. And there are other interactions like with wildcards, et cetera. So it's not all about adding features. Since 2017, we've also been doing a lot of refactoring. This work is pretty much invisible to users, and honestly, it's pretty hard for me as a feature pusher to really appreciate the value of it. And in my fairly long career as a product manager, I've gotten kind of skeptical of refactoring. Software developers always want to rewrite things, make them a little bit nicer. But there's a risk anytime you change the software. And I wanted to be able to see that it was actually doing something useful. So we started the refactoring back in about 2017. We refactored RPZ, a couple of major functions, query find and answer response. Then in 2019, we started to tighten up our system level requirements. We dropped support for Windows. Then we moved on to refactor a lot of our crypto support. Now we require OpenSSL, it's mandatory. I'm going to talk a lot more about the refactoring after that of the task manager, the interface manager, and the dispatch manager. Hopefully, it's not going to sound as much like gibberish as that did. And we're continuing to do refactoring. This year and next year, you're going to see us refactor the primary database structure and bind. So the arguments behind refactoring, they're pretty easy to understand. Bind has a real problem with code complexity. There have been at least 4 dozen primary authors of Bind over the past 25 years, and the DNS itself is very complicated. Been a lot of changes in both hardware and operating systems. The core design of Bind dates back to really just a different era in computing. And there are some real opportunities to take advantage of these new operating system and hardware platforms. In particular, we wanted to adopt some standard Linux libraries and reduce the amount of code that we have to maintain ourselves. And finally, there are a lot of features that are now obsolete. So on the topic of complexity, back in 2017, one of our developers did some analysis using a kind of a derivative of a very well-known technique called the McCabe cyclomatic complexity index. And this is a way to quantify how complicated your code is by looking at how many different paths through the code you could take. If you look it up on Wikipedia or something, it's well described. Actually, this blog post at the bottom gives a lot more information about our analysis and what the McCabe index is. But basically, all you really have to understand from this is that this guy said that anything that had a complexity factor, any function had a complexity factor over 20, you should consider refactoring it. And at this time, we were at Bind 910, and we had over 500 functions that were that complex, and we had more than 2 dozen that had a complexity factor over 100. So this is a fairly massive problem. So the very first one that we refactored was called Query Find. Before we refactored, had a complexity factor of 453. We got that down to below 50. In selecting this, one of the reasons we selected it was the most complicated function we had, but also we did an analysis of our recent CVEs, and this was the source of a bunch of our recent CVEs, and obviously those two things are related. So just to go back to this point about the change in the computing landscape and the platforms we're running on. When Bind was first developed 25 years ago, a really fancy hot server might have 4 CPUs, might have a 100 megabit network interface, might have a 500 megahertz clock. And honestly, a lot of people ran the DNS on their old machines anyway, because it was not a very expensive thing. The original Bind developers also were very committed to making Bind run on as many platforms as possible. So when I joined in 2013, and up until just a couple years ago, we still supported AIX, HPUX, Solaris, and Windows. So in order to get Bind to work on all these platforms, the Bind developers built a lot of components that are now really part of the standard operating system. So Bind really was almost an operating system. The other thing is, today you can get a machine that's got 256 cores. I'm not a hardware person, but I know that when you've got a server that's got a lot of CPUs, you really expect the performance to kind of come along with the hardware. You're expecting to see a lot more throughput through a machine like that. And Bind wasn't taking advantage of that at all. Even though it was multi-threaded, when the traffic comes in, all of the incoming traffic was actually received by a single thread that would then hand off the work to another thread. And as you got more and more CPUs, it was increasingly likely that that other thread was going to be on a different CPU. So we're context switching all the time, and this was a major bottleneck. So in 2017, we kicked off what was really the most ambitious refactoring we've done to date. In fact, I remember before we started working on this, when we were talking about it, actually, this didn't start till probably 2019 or 2020. When we were first talking about it in 2017, when we established kind of a hit list of things to refactor, a lot of the engineers thought that refactoring the network interface is simply going to be impossible. Anyway, we had a new guy who was ambitious, and he undertook it. So what we did is we replaced a lot of the ISC code with libuv, which is not maintained by ISC. It's a standard Linux library, which we don't have to maintain, which is great. We wrapped around that a loop manager. The loop manager assigns work to an individual CPU. All the work is now basically pinned to a CPU, so we've achieved some much better performance with a CPU affinity. And then underneath the, after the loop manager starts up the loop and assigns some tasks, these net manager spawns networkers, and these are the things that terminate the TCP or UDP. They understand DNS, TLS, HTTPS. So we really solved the context switching problem and removed a big barrier to higher performance. So the software engineers kept going on about how we now had the MultiListener model. And for a long time, I really did not understand what that was. And so I'm just going to share the analogy that helped me understand the benefit of this MultiListener model. Perhaps this is on my mind because I had to travel to get here today, but the classic Bind network manager was like an airport queue, where everybody waits in a line, and then when you get to the head of the line, you go to the first available desk. This is what we call the single listener model. This isn't a bad model. Everybody gets the first available agent. When they're at the head of the line, But some of the agents are actually waiting to get work. So an agent becomes free, and then somebody comes over to the agent to be helped. So it was slightly inefficient. The agents were waiting a little bit. These agents represent your CPUs, which also would be waiting a little bit. So there's a little bit of inefficiency built in. Plus, of course, as at the airport, after you finish checking your bag, then you go get in another line to have your carry-on luggage screened. When you're done with that, then you go get in another line. You buy your duty-free or whatever. You get in another line to have your boarding pass examined before you board. So there are multiple different lines you're waiting in. So with the new multi-listener model, this is part of the network refactoring, it's like there's a whole lot of separate lines. So when the traffic first arrives, you get in a line right away. You get in a queue for a particular agent. And this is much more efficient overall because the agents are never waiting. They're always working. One downside of this is you can get in a line that's slower than some other lines. If somebody in front of you doesn't have all their paperwork or they have some other kind of problem, you can get in a slow line. So you might wait a little bit, but overall, the traffic is handled more efficiently because none of the CPUs are ever waiting for work. So we rolled this out with 2016 and with Bind 9.16, and it was supposed to be this huge improvement. But almost immediately we started getting reports of problems. These problems varied. They were almost always load related, under heavy load, which made it much harder to find them and much harder to troubleshoot them. The developers did eventually hunt them down and fix them. But to me, this was really disconcerting, and I felt like I kind of lost faith in the whole refactoring project because it seemed as if we had broken things that we didn't understand. So the real truth was we had actually only halfway completed the refactoring. So a bind is both a server, an authoritative name server, and a recursive resolver. We had implemented this fancy new multi-listener model with libuv and the new network manager for requests that we received. So as an authoritative name server, we had, relatively speaking, blazing fast performance. However, for queries that we were sending out, we were still using the old infrastructure, the old bind task manager, the old homegrown socket code. So as you can imagine, we've got these queries coming in really fast, and we're sending out queries for resolution much slower. You can probably guess what some of the problems were. In practice, anytime we have to do recursion, we are also sending out queries before we can complete the work. So we effectively kind of had both kinds of lines. We had the one long line that the inbound queries were waiting in, and we had the we had the one long line to send out queries, and we had the multiple listener model on the inbound queries, inbound requests. The other thing was, we noticed we were using twice as much memory. And this, of course, is because we were maintaining both the old network model and the new network model at the same time. And the orange line at the top there, I highlighted it. That's by 9.16. The green line at the bottom, that is both the predecessor, 9.11, and the successor versions, 9.18 in the main branch. So twice as much memory. The developers weren't the least bit surprised. What would you expect? We're running both network models. But I had no idea of this. I hadn't expected it. The users hadn't expected it. And I didn't want to have another unexpected consequence of refactoring like this. And so I started to really question, is this refactoring progress? As I mentioned before, all change in software, especially complicated software, has a lot of risk. are the developers just doing this because they want to rearrange the deck chairs on the hypothetical Titanic? What's the user benefit? And finally, how much of this have we already refactored, and when are we going to be finished with this process? So first I tried to figure out how old is all the code. I thought it must be possible to run some kind of a program that will tell me for every line, is this a line that's from 2002 or is this from 2019? It turned out this was not helpful for a couple of reasons. First of all, even though it's a pretty picture, you can't tell what any of those lines of code are doing. And second of all, frequently we're rebasing, and so this isn't even as meaningful as it looks like it might be. So then I tried to nerd snipe the developers into coming up with a functional diagram for me. These are two of the more adorable options I was given, but as you can probably tell, neither of them were the least bit helpful. I did get a couple that were a little bit more helpful. This is just a small portion of the bind code, I was told. So here's a little snip. Well, so this is also not a helpful, useful level of detail. So what I was looking for was something that I could relate to functionality in the system. So I finally just tracked down one of the developers and interviewed him. This is not a very elegant picture, but at least looking at this, I can understand what all the functions are. So the top part, of course, is the network interface that I already mentioned that we refactored. Below that, you've got these blue sections. On the right side, the darker blue section represents the elements that manage queries coming into named. So they come in through an interface manager. The interface manager receives the request, hands them off to a client manager. Then the separate clients go ahead and perhaps forward the query to the resolver, which runs around back and forth between the address database, the validator, the cache, whatever comes up with a response, goes back and wakes up the client, and then the client sends it back out. On the left-hand side, the dispatch manager, those are for queries that are coming from bind, they're outbound requests. So for instance, a request that came to the resolver, if it required resolution, the resolver would go to the dispatch manager and send that outbound. Then we also have something called the request manager. So the whole gray area in the bottom is a server object. Within the server object, you have multiple different views, and each view has got its own resolver, validator, address database, zone list, cache. The request manager is there for requests that are generated basically internally to named. So this would be a primary sending out a notify, or a secondary requesting a zone transfer, that sort of thing. Anyway, my color coding isn't great, but the things that are in gray, or primarily gray, are not yet refactored, and the things that have some color are refactored or entirely new. I wanted to find out, though, how much of the code had actually been refactored. And this is a little bit approximate, but we looked at the size of the different files and what were the functions in them and which had been refactored. And please don't do the math because it does not completely add up. But the bottom line is about a third of bind has been completely rewritten since about 2017, 2018. On top of that, it's actually quite a bit smaller. So we've lost at least, or removed at least 75,000 lines of code, and even more files than that. So our new, it's not new since 2013, the director of the DNS team, Andre Suri, he just loves to find and delete obsolete code, dead code, and that's just a happy project for him, removing the dead code. And that, along with the refactoring, where, for instance, we removed the code that did what libuv does now, we've got significantly less to maintain. I mentioned that the network interface was really a bottleneck. We actually have found that since the refactoring, the performance for an authoritative name server has really improved dramatically. So on this chart, the yellowish bar is the performance of 9/11, which is prior to doing the network refactoring. And the green, blue, and red are all since then. The green is the current main branch. The blue is 9/16, and the red is 9/18. So you can see about a 50% performance improvement. We run this with a bunch of different test cases. This particular test case is using 1 million small zones, but we also have test cases for the root, for a single very large zone, for other test cases. All of them are much better. Testing resolver is a lot more complicated. We have got a very sophisticated resolver testbed now. And by the way, one of your colleagues here in the Nordic region has been giving us sanitized PCAPs. So we are using actual real traffic from an ISP in your region to perform all of our resolver performance testing against the live internet. Anyway, this is a very complicated chart. It's too hard to explain in half an hour, but unlike most charts, the farther to the left you are, the better the performance. And on this chart, the very rightmost line, the blue line, is 9.11 before we did the refactoring. And the lines to the left of that are each subsequent train since then. And so we are reducing the latency. I think the difference may not be quite as dramatic as it has been on the authoritative side, but clearly we are improving the performance. So what's next? What is left to refactor? The big project that we're working on right now is replacing the database. We have a red black tree database today that is used for zone data, for the list of zones, for the data in those zones, as well as for the cache. And we're refactoring that this year. We've actually just a week ago committed the first big commit here. And this work is really all due to Tony Finch, someone who has been on the Bind team for just a year. We hired him from the University of Cambridge, where he'd been doing research on QP tree and other data structures for quite a few years. He has already implemented the QP tree for NSD, and the NOT team also has independently implemented it for NOT. And he's been doing a lot of test projects to compare both the memory footprint and the speed of the QP tree versus the red-black tree database. And I'm pretty confident that this is going to be a big improvement. Also, we've learned quite a few lessons from the network management refactoring. First of all, we've switched already to a two-year cycle between major releases to give us enough time to complete the refactoring before we issue a new stable version. And second of all, we have a plan to make this new QP tree an option versus the red-black tree database for each of these functions: the zone, the cache, and the zone list. This change, it may improve performance, but the primary thing we're trying to do here is reduce conflicts and blocking. So, for instance, we have had issues, back when we first came out with response policy zones, which is a DNS filtering technique. People would update their response policy zone, which is basically like a block list, maybe daily, weekly, and now people are updating it every 5 minutes. And processing those updates was blocking Bind for doing other operations, and obviously that is not tolerable. So that's an example of the kind of blocking that we're trying to reduce or eliminate with the new database. That's all I'm going to say about the refactoring. I just wanted to add a few things about the overall project health. We still have all of the committers to bind, our ISC staff. You know, it's still closely managed, but it is an open source project. And we now have a completely open repo. We have an open issue tracker. Anybody can go online, look at our GitLab, see what we're working on, watch the pipelines. We have started maintaining a whole slew of our own packages. So you don't have to use, a 3-year-old version of Bind just because that's what's provided in your favorite OS distribution. We've got monthly maintenance releases, very regular, very predictable. I mentioned the biannual stable versions. We support every version now for at least 4 years. And our docs are online now. They've been reformatted, updated. We've got hyperlinks in there, more intro content. I'm really proud of our QA efforts. We now have 4 full-time QA engineers and a part-time intern. And what we're doing today is just light years beyond what we were able to manage back in 2014. The continuous integration, it now runs about 70 jobs for every version of every merge request. We're running every code sanitizer and every static analyzer you can get. I'm sure this is not an exhaustive list, but these are the ones I know about. We run performance tests daily. We have one engineer who really specializes in performance testing because this is quite an art form. RESP-Diff is another tool we've been using that allows you to compare 2 different versions of Bind and make sure you get the same responses. We do fuzzing. We have a regimented 2-week process after we have a code freeze prior to each monthly maintenance release, during which we investigate all the failures and run through quite a checklist. Despite all this, we do still have bugs, and we do still have CVEs. But now we're finding a lot more of these in-house, which is really an excellent sign. We have raised the bar for the full security response. So now you can only count on us always doing that if the CVE has a severity of 7 or above. Sometimes we still do it if the CVE has a lower severity, if we think it might affect a lot of people. A lot of our vulnerabilities, almost all of them, are cases where Bind will shut down because it gets into an unknown state. And most of the time, this is only possible in a very specific set of circumstances, like with a specific configuration. And so based on how common we think that is, we kind of throw that into the mix in deciding what the patching strategy should be. But we do still take our CVEs very seriously. We have a well-documented procedure for triaging, assessing, patching, and announcing these in Bind. So in conclusion, I just want to say that even though Bind is very old software, we have a really vigorous team. We've got an excellent group of folks working on Bind. The whole project is a lot more transparent than it was 10 years ago. The features that we have added are mostly in favor of making it more robust, particularly against denial of service and abuse. We have done what we can to simplify the maintenance, particularly simplify the operation of DNSSEC, improve the documentation. And the work that we've done in modernizing the infrastructure is really improving performance. And it's also allowed us to add new transports. I mentioned we've already added DNS over TLS, DNS over HTTP. We're looking at DNS over QUIC as soon as those libraries are stable. We do encrypted transfers already, XOT. So I think that despite the fact that it's very old software, it's really very well maintained. I have a few references here I would recommend. Andre wrote a blog on bind memory management. This is another thing I didn't mention that we did in the refactoring. We had written our own memory allocator, one of the many homegrown bind libraries that we replaced with the standard library. Tony Finch has quite a few blogs on his personal blog site. He's got the best address on the internet, .at. But he's written quite a few blogs on his QP tree work for anybody who's interested in the real nuts and bolts of that. We've gotten a number of blogs from our QA team, which I think really highlight what an expert team we have right now. And the last link is just to a retrospective of what we've done in the past year. I just have one closing thought. This is not on the topic of bind. It's just a public service announcement. I know a lot of you are ISPs. A lot of you are probably running ISC DHCP, also known as DHCPD. And last year we announced its end of life. I know nobody wants to upgrade their DHCP, but you should really consider that. So if anybody has any questions. Another topic I'm also very interested in, if anybody wants to talk to me about this at the break, is the pending Cyber Resilience Act. So I think that's going to be very important for open source, and I'd love to chat with anybody who is interested in that topic.
Hi. So I do a lot of DNS stuff.
Excuse me?
I do a lot of DNS stuff.
Okay.
My name is Johan Stenson. I gave up on bind a number of years ago. And I looked for alternatives and I switched a lot of stuff around. I have never seen a more impressive turnaround of an open source software project. I'm back to bind. It's really, really nicely done.
I'm glad to hear that. We have one engineer who actually was one of the authors of the OpenDNSSEC project, who has really just been focusing on this new key and signing policy tool for maintaining your DNSSEC, and it's good to hear that. Thank you.
The lack of CASP was one of your major problems.
I know. Anybody else?
I could then have a question. I'm at Netnod, so part of iRoot. The other competitors, which is much younger, have developed the authoritative part separated from the resolver. Do you have any thoughts of splitting bind into two different softwares, or do you see it as a better software combined, or would a split be too hard to do?
We have considered that. So the question was, have we considered splitting the authoritative and the resolver? First of all, there are a lot of advantages to having them both there. There are functions of the resolver that the authoritative server would have to use anyway. And we haven't really seen an opportunity there. There are some other similar massive changes we've considered. We've talked about becoming, more child-centric. Right now we're parent-centric, if you know what that means. We've talked about Rust. Everybody says Rust is better than C. You should rewrite everything in Rust. There again, you don't get any advantage unless you do the whole thing. So I guess the answer is no. We're not looking at that right now. I'm very conscious of the other systems out there. I do think it's great that there's some heterogeneity, there's some choices. I was reading the Unbound mailing list recently. I recognized a well-known person from the Bind users list who'd started using Unbound, who was having trouble trying to run both Unbound and NSD on the same system. And he needed them on the same system because he had been using Bind and he was used to having them both on the same system, and he was having issues with that. And I think it's actually, there's not enough heterogeneity, honestly, between the different systems. And So no, we're not planning on splitting that at the moment. It's certainly something we have considered and looked at, but we don't really see the advantage.
Yeah, and we at Netnod often talk about diversity, so it's good that not all the software work the same. So it's not a complaint, it was just a question what you're thinking of the future. So
No, that's all right. You're welcome to complain. I've been hearing complaints about Bind since I came to ISC, so I'm pretty used to it. Okay, I think that's it.